Hi everyone, this is Addison Alford from the University of Oklahoma. I was the 2013 Holling Scholar, and this is the presentation that was given at the University of Alabama at Huntsville, as well as the National Severe Storms Lab. I'll go over a brief introduction and background for the presentation, as well as the methods that we use to analyze the data, and I'll go over the results and the conclusions of the warning analysis and the radar analysis. So why do we need to discuss these warnings? Klockow and Pepler found that after April 27th, folks did not understand that a tornado warning meant they needed to take action. This, of course, can lead to increased injuries and fatalities. And if we can provide a more accurate warning system, then we can cut down on those injuries and fatalities and possibly spur more action out of the folks that normally did not or will not take action. And of course, this will all lead to a more weather-ready nation as set down by NOAA's long-term goals. The question that needs to be answered here is about the previous storm classifications. They were very broad, and a more robust classification system could lead to a better understanding of where the office is going wrong in its tornado warnings. What I mean by the previous classifications is the three classifications that tornadoes and warnings were classified as: QLCS, supercell, and tropical. These made up 229 warnings for QLCS and 417 warnings for supercells, which are both very broad areas and need to be re-examined further. QLCS tornadoes, they're very difficult for the radar operators to see as the mesovortex generates from the ground upwards, and there may be a stronger correlation with rear inflow jets and tornado genesis. So what we did for the classifications was divided it into these categories. However, I'll go over non-supercell line and marginal supercells in this presentation. We also used GR2 Analyst with archived NCDC data, as well as archived AWIPS data from the office. We used this to examine all 721 tornado warnings, and the storm data was found with the NWS verification website. The results that we got were 26.9% of non-supercell, 26.9% of tornadoes were non-supercell line, with a false alarm ratio of nearly 76%. Almost 10% of all false alarms were also marginal, with a false alarm ratio of almost 100% and a POD of 10%. And there was only one tornado caught out of the 10 marginal tornadoes. Both of these are very large areas in the database, and they warrant more study since they make up such a large percentage of the false alarms. If you remove all 53 of the marginal supercell warnings, you can reduce the false alarm rate by almost 2%, and your POD would only reduce by less than 0.5%. Non-supercell line tornadoes, again, they have a very high FAR and low POD. This was a false alarm case. However, you can see that the rear inflow jet remains elevated and the mesovortex never ascends. So overall, if you look at all 68 QLCS tornadoes since October 2007, 76.5% of them actually had a defined descending rear inflow jet. One tornado did not, in a non-supercell line case. 61.3% of false alarms did not have a descending rear inflow jet. And if you consider both of the tornado cases and false alarm cases, there were cases which the radar did not allow us to identify it correctly, either due to the radar beam being perpendicular to the radial velocities, or the radar was just simply too far to see a descending rear inflow jet. This does, of course, offer more problems. However, there could be more study that could be done. So in summary, the reclassification that we did on the warning database allowed us to understand where Birmingham was going wrong in their warnings. The results of that allowed us to study the radar signatures of these storms more closely, and the marginal supercells yielded very weak reflectivity and weak rotation throughout their lifetimes, and a concentrated or localized descent of the rear inflow jet was found in tornado cases and was not in non-tornadic cases. So the conclusions from this, Birmingham can now use the new classifications to understand where they're going wrong in their warnings. The rear inflow jet signature could be used and will be shown in some, what are we going to call those? Forecasting cards?
I don't know what to call that.
Oh well, I just won't say anything about it. The rear inflow jet signature could be used in operational mode. The plan view is slightly more complicated to look at, but that will be discussed later with Kevin and with the aid of several forecasting cards that Andy and I are coming up with. The reason that the rear inflow jet may have a correlation with tornado genesis is after it hits descends into the ground. Law of, oh God, what's the law? Conservation of mass. After it descends to the ground, conservation of mass says that that air has to go somewhere, and it could be responsible for actually deepening the cold pull after it descends into the ground, or it could enhance near surface vorticity and allow for greater convergence near the surface.
Well, with tornado formation or tornado genesis, what we're finding and what other people are finding is that you might have a rotational lock, but it's a rather weak rotation. And what's the characteristics of the surface are the important elements that trigger tornado genesis. That could be topography, that could be variations in surface roughness, or it could just be surface roughness itself. And what we're finding is that circulation, weak circulation might be a lock, but what happens is the formation of a tornado occurs down in the lower several hundred meters of the atmosphere and then builds upwards. So according to that research, tornadoes don't really touch down and lift off. A better terminology would be tornadoes form down at low levels and dissipate at low levels.